Hello to everyone. This is a relatively elementary stream today, so anyone who's played the natural numbers will know that you can do this. Inductive minat. We can write 0 minat, and then there's a successor minat to minat. Here's Peano's definition of the natural numbers. And when you think about it, so if we go into that minat namespace, namespace minat, and minat, there, now we have access to Z and S. So let's make an example of a natural number. Well, how are we going to do it? I guess we can't use S. I mean, we've got to start with Z, right? There's an example of a natural number. We could check Z. There you go, Z's a natural number. And then once we've got one, we can make lots more, right? Check kind of S of Z. There you go, that's a natural number. And check S of 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 Z. That's going to be a natural number, you can see. There you go, 1, 2, 3, 4, 5, 6, 7, 8 S's. But you can also see equally easy that these are the only natural numbers there are, right? You can't make any more natural numbers because you've got very limited, you've got limited interface here, right? You've got Z, which is a constant natural number, a 0. And then the only thing you can do to a natural number is make a new natural number with S, you see. So this is, in some sense, quite a limited system. So let's make a better collection of numbers. So what about this? Inductive supernat. There, where we can have Z is a supernat, and we can have, let's have S, just the same before, supernat to supernat, and then let's have another one, T, from supernat to supernat. Why not? Oops. There. So what is this? More powerful system of numbers. Because there's more than one way. So now you can, numbers have got two successors now. We've got 0 and then one, S of Z and T of Z, right? So let's look in the supernat namespace. There, and now we can check Z. That should be a supernat. There you go. It is. But we could also check S of Z. That should be a supernat. It is. But then here's another one, T of Z, which is a different supernat. There. And so now we can make all kinds of interesting numbers, right? Check S of T of T of S of T of S of S of S of T of T of Z. There you go. So you can see this is a much more rich system. It's some kind of, clearly some, what is this? This is clearly, clearly just numbers, right? Count the S's. There. And what's this? This is clearly some, this is clearly some rich binary tree, right? With a top node of 0, and then we can keep going in the S direction or the T direction, and make all kinds of, some rich, complex, subtle structures. So there you go. So now let's actually have a think. How can we understand things like S, T, S, S, T, S, T, S, Z, right? Well, the first thing that we notice, they all end in Z. And so really, we could just remove that Z. So really, a term of this type is just, more like a string of S's and T's, right? There. May as well forget the Z. A string of S's and T's. And so what can we do with a string of S's and T's? Well, actually, I mean, imagine kind of S is 0 and T is 1. It's a string of 0s and 1s. There. So it's a binary number, right? So in fact, this super nat thing is suddenly looking a lot like nat, right? Is super nat actually equal to nat? Well, there's an issue, isn't there? Because s is 0 and t is 1. So binary numbers kind of, I don't know, 1 0 0 1 and this thing here are the same, right? So there's a catch, right? But STTS, no, T is 1. TSST is not the same as 1, 2, 3, 4, 5, 6, 7 S's and then T and then TSST. Right? They're not the same. And so our little idea about making this a binary number, so we've got an issue. We can't start with zeros. So we're supposed to start, do binary numbers start with 1? Let's look at the binary. Here's binary numbers. 0, 1, 10, 11, 100, 101, 110, 111. There. Now, other than 0, they do all start with 1. And the 1 is somehow an indication. It's like, let's get going, right? That's the point of the 1. It says binary number actually starts here. So maybe that was Z then. There, because our Z said, you know, string starts here. So how about Z equals initial 1 and then read it backwards. There. So a general number is something like Z TSST, whatever, Z SS SST ST there, and this should become so this is backwards, and this should become 1 1 0 0 1 0 1, which is binary for 37. So there's our dictionary, and maybe actually this is just a way of doing binary. So supernat is just binary. There. So let's do the definition then. Binary nat. So it's like I called it Z. Let's call it 1. So this is an inductive type. Inductive binary nat. So 1 is a binary nat. And then we've got bit 0. This is mapped from binary nat to binary nat. And this means add a 0 on the end. There. And bit 1, binary nat to binary nat. There. So example, binary nat would be, let's go into the namespace. Where are we, by the way? Did we? Oh, I haven't imported oh my goodness me, have we got anywhere? Import tactic. Lovely. And now where are we? I'm in binary nat, wonderful. So end binary nat. So an example of a binary nat would be what we do 1, and then what do? We double it, and then we double it again. So that's so this is 4, and then we double it and add 1. So that's 9, and then we double it, and that is 18, and then we double it and add 1 there, and we get 37. So that's how we're going to do binary nats. Great. So maybe the first thing we should do is we should, I don't know. So now we need to make an API, right? For binary nats. So, you know, let's play the But these, do you notice this starts at 1? Notice that these nats start at 1. We can't make 0. So they're the British natural numbers, right? So we need to make an API for them. So let's play the British natural number game. So one thing you know about the natural number game is that it's extremely important to set, I guess, successor. Successor was important, right? Successor was everywhere in the natural number game. So let's define successor. Let's go from binary nat to binary nat. And how are we going to define it? We're going to do it by cases, right? Let's say what the successor of 1 is. The successor of 1 is 2, which is bit 0 of 1. The successor of bit 0t, the successor of that would be bit 1t, right? It doesn't like that. Why does it not like that? Shall I put it in brackets? Oh, it likes that. Great. What's the complaint now? Yeah, the complaint now is that we haven't finished yet. And bit 1t, what's the successor of 2t plus 1? So the successor of 2t plus 1, so this is IE double, right, this is IE double. And this is double and add 1. So the successor of 2t plus 1 is 2t plus 2, right? Which is 2 times t plus 1. So the successor of bit 1 of t seems to me to be bit 0 of suck of t. There we go. So there's our definition of successor. So it would be nice to have, I mean, we don't have a 0, unfortunately. We've got a 1. So let's make the 1. Instance has 1 binary nat. And that's just going to be binary nat dot 1 there. And so there's that. And maybe actually I could use, if I put that there, could I even use this? Could I even do this? This looks nicer, doesn't it? There you go. Maybe we should have a simp lemma. Simp. How do you make simp lemmas like this? Simp lemma 1ec1. 1 def 1 equals 1. And that's true by definition. And I'm hoping that the simplifier will now change word 1 to number 1. And maybe we should also do, while we're here, lemma 1 suck. The suck of 1 is bit 0, 1, and that's true by definition. Maybe we should do all of these actually. Simp lemma suck bit 0. This should probably be called suck 1, right? And suck bit 0 t. Oh, we need notation. I'm not going to write binary nat. Right, what notation should we use for the binary nats? How about notation? I don't know. P, because they're positive. P, there you go, is binary nat. It can be projective space, so it's /BBP, in case anyone's wondering. Black bold P can be binary nats. So suck bit 0 of t in P says that suck of bit 0 t is bit 1t, and that's true by definition there. And then maybe we should also have suck bit 1 that says the suck of bit 1 of t is bit 0 of suck of t. bit 0 of suck of t. And that's also true by definition. So there we go. We've trained the simplifier to do some basic things with successors. And so now, I suppose, what did we do in the natural number game? I suppose the next thing we did was addition. So let's define addition. And so now let's define addition of binary numbers. And so this is literally column addition, right? Column addition. So how are we going to define column? Let's define add. So what is this? Binary nat. Oh, can I use notation now? P to P to P. And how am I going to do it? Well, I'm going to do it term by term. I guess I could cheat with the ones, right? I could do 1. I mean, 1 is just suck, right? 1b colon equals suck b. There, and b and a1 is also suck of a. But now let's actually get onto the column addition part. How do we add bit 0a, add bit 0b? How do we add those things up? We could do some spaces now, couldn't we? Just make it look nice. There. So how do we add up two binary numbers? Wrong line. How do we add up two binary numbers that end in 0? Well, the result also ends in 0. And then for the rest of the stuff, we just add them up, right? Add AB. And bit 0. Oh, so this is kind of easy, right? Bit 0A, bit 1B. How do we add together two binary naturals? So the first one ends in 0 and the second one ends in 1. Well, we claim that this ends in 1, and then we just add A and B. And similarly, bit 1A added to bit 0B is bit 1 of A add B. And then the last one, bit 1A add bit 0B. If I just put sorry, does that now compile? No, it's because I've got a bit 1. Does that compile? Yes, that's now compiling. So how do I add two binary numbers that ends in 1? Well, I guess the trick is that it ends in 0, but now we have to carry 1, right? So 1 add 1 is 0, carry 1. So instead of now adding A and B, I have to add A and B and then take the number after. Suck of add A, B. So how about that for a definition of addition? There. So there's my definition of column addition. So, and now, you know, inspired by the natural number game, let's prove basic stuff. I don't know, let's prove suck egg add 1, right? That's something that we do pretty early on. Do you know what? I'm going to prove the other way. So lemma add 1 x suck. I think the successor is somehow simpler than addition. So let's make this a simp lemma. Let's try some experiments. Let's make this a simp. Add 1 x suck. And what's the theorem here? The theorem is that if B is a binary nat, let's make notation. Instance has add binary nat is just going to be add. So add 1 x suck says that B add 1 equals the suck of B. And what's the proof of this? It might be refl. Oh, this should be A's. I'm going to go for A with the first. Add 1 x suck. A add 1 x suck of A. Is that true by definition? Let's try it. No, it's not. A add 1 x suck of A. Do you think if I put that If I put that one before that one, it would be. No. Okay, well, it's not true by definition, but it's going to be true by cases A, REFL. Yeah, that's worked. Because all we have to do is check that it's true in every case. And similarly, let's do one add X suck. There. B add 1 is suck of B. Let me, I'll show you what just happened in that last one. Is case, I bet cases B REFL does it. Yeah, that's a proof, you see. I've got no warnings and no errors. But let me just show you let me show you what's going on here. Cases B, then we should have 3 goals, right? You know, when you do cases on a natural number, you've got a 0 or successor case. Here we have 2 successor cases. So this one says 1 add 1 is suck of 1. And so that's just the case. You see, that's just true by definition, right? The definition of 1 add 1 is suck of 1. So this one is REFL. And now what have we got to prove next? So there's our 3 cases. What have we got to prove next? Oh dear. We've got to prove bit 0 B add 1 is suck of bit 0 B. But you see, this is just true. This is just true by definition, right? So this is true by REFL. And similarly, this, whatever this says, bit 1 B plus 1 is suck of bit, this is also true by definition. So all these things are true by definition. Oh, thanks. Have I got it wrong? Thank you very much. Let's see if the proof still works. Yeah, the proof still works fine. And you can see in all cases it's just true by definition. So there's suck ek add 1. And now I guess the next thing we proved, next on the agenda, in the natural number game, I mean, we somehow had add 0, but somehow, but those are going to be called add, you know, we can't do add 0 because there isn't a 0. So we're going to do add 1 and 1 add. Next on the agenda in natural number game is add a sock. But this will involve 27 cases there, and some induction as well. So in stark contrast to the natural number game, where you just did an induction, because the natural number game, if you wanted to work with A add B in the natural number game, the definition of add depended on whether B was a success, you know, depended on whether B is 0 or a successor. So 2 cases. But the definition of addition here involves knowing how A and B were born. So you can see that this is a pain. In fact, let's do a simple example. Example. Well, maybe I'll leave this as a lemma. So add a sock 1 1. So let's have A in P. Let's do A add. Which way around do we normally do it? A add 1 equals A add 1 add 1. There. Begin, end. So there's a special case of associativity when both of these things are 1. And I guess we just have to do, we might just have to do things by cases. Cases A REFL, how about that? Oh, it doesn't even work. Cases A simp, let's try that. And that has also failed. So simp has failed to do, well, let's see what's going on here. What's hard? Cases A. Oh, maybe we need to do induction on A. Let's try induction on A. And now let's try simp. What about that? No, but it's still struggling. Okay, so let's have a look. Induction A. The first case, I've got to prove 1 add 1 add 1 is 1 add 1 add 1. So that is surely REFL. So induction A with BHB, BHB or something. So what have we got to do in this case? What have we got to do here? We've got to do bit 0, B add 1, add 1 is bit 0, B add 1, add 1. What happens if we use the simplifier on this? The simplifier is thinking for a very long time. Why did that take so long? Bit 0 of suck B, is bit 0 of B plus bit 0 of 1. And the simplifier didn't know that. Is that really what happens? Let's just go through this. Bit 0, B add 1, add 1. Rewrite bit 0, so is the issue, so it seems to me that the simplifier will turn the left-hand side. So if I rewrite bit 0 suck, it will turn the left-hand side. Oh, I failed to rewrite bit 0 suck. What did I call it? Oh, suck bit 0. Suck bit 0. If I rewrite suck bit 0, oh, that's also failed. I'm not doing very well here, am I? Suck bit 0. Oh, I see. It's bit. I need to rewrite add 1x suck. There. And then I need to rewrite it again. So let's simp only add 1x suck, and let's see what happens. And now we can rewrite suck bit 0. And that has worked. And now we can rewrite suck bit 1. And this says that bit 0 of suck B is bit 0 B plus suck 1. Well, there you go. So this is trickier than you might think. Bit 0 of suck B is bit 0 of B plus suck 1. So it says 2 times A add 1 is 2 times A add 2. I wonder, So yeah, what are we going to do here? We are going to, I'm just thinking of a good way of attempting to approach this. Why doesn't this work? Induction A. I wonder if I'm missing some simp lemmas. Maybe I should. I want to get the simplifier to do this. I want to get the simplifier to do this. So I wonder what I should do. Maybe I should tell it what 1 add 1 is. Well, when we do induction and then we do simp, and then let's try refl. Let's try this and let's see where we actually get to. And look at this. So it fails to do. How are we going to do these cases? Bit 0 B. It's not simplifying these. I see what we're doing. Look. This is what we're missing. Why don't we tell it lemma bit 0 add bit 0. There. Why don't we tell it this? Oh, what is it? Okay, great. So this would have A and B in P. Let's tell it bit 0A add bit 0B. Add bit 0B is bit 0 of A add B. There. And, oh, I need notation. There. Oh, this hasn't gone well, has it? What's the error? Oh. Oh dear. Bit 0A add bit 0B. Equals bit 0. Whatever's the problem with this? Type expected at bit 0A add bit 0B. I need help. Someone from the chat can tell me what's wrong. Type expected. Have I just got some colon in the wrong place? Oh, there it is. Wonderful. Great. Let's prove 4 of these. Bit 0 add bit 1. Bit 1 add bit 0. And bit 1 add bit 1. And let's just say exactly what the answers are. So this is a 1. And this is a 1 and this is a 1. And this is a suck. There. And this is a 1 here. And these are both 1s there. And now let's see how the simplifier goes here. And now the simplifier can prove it. Great. So this is a very simple case of associativity. But in some sense, even that was hard work. Look at that. The simplifier is really thinking. Let's put a full stop there. Hopefully that'll stop it compiling it. And so now let's try this one here. There. So that's of A and B. What's this called? Add a sock 1. And this one, actually, because we know, if you think about this, I don't really want to call this add a sock. I mean, I could call this add a sock 1. Okay, I mean, let's try and prove it. Let's try induction. Let's just do the stupid thing. Induction B, case is A, simp refl. Let's try that. And it's not worked. It has not worked. Do we need the induction? Suck of, oh, you see, we need this, it's stuck on add suck. You see, it's failed to do add suck. Suck of A add B. In the natural number game, this is true by definition. A add suck B is suck of A add B. So I guess we should, in fact, this is add suck, isn't it? So this fails. Try refl there, and then let's see how many goals we actually ended up with. We ended up with 2 goals. So sorry. So there's some failure, but you see, but add 1 is suck. So this says suck of A add B is A add suck of B, right? This is just add suck, right? So add suck is something that we're going to have to, mess around. It's going to take 10 more minutes, and then associativity itself will be, lots and lots of cases. So don't really want to do it. Looks sort of straightforward but long. Okay, and so here's another idea. Binary nats are just positive natural numbers, right? And we've already proved that addition is associative on natural numbers, because we proved it, in the natural number game, right? And it was easy. So why not let's deduce associativity of binary plus addition with carry, right? From associativity of addition. So let's do that. So what's the link between the natural numbers and the binary natural numbers? And I guess it's this. So let's define of nat. So let's have n a natural number, and let's have hn a proof that n isn't 0. And let's define an element of P. So how are we going to do this? I guess we could do it using the equation compiler. We could say, where does 0 go? And we don't know where to send 0. Ah, I see. So we could do a natural number which isn't 0 to P. And I shouldn't name it. We could define this using the equation compiler. We could say, where does 0 go? I'm not sure where 0 goes. Where does 1 go? It goes to 1. I mean, I'll put binary nat.1 just so we're absolutely clear. I see, these are issues. With 1h, we have to include the proof that 1 isn't 0. And now similarly, we'd have m plus 2 h could be it could be, I guess it could be suck of nat m plus 1 something. You see, this is kind of a pain, right? So now I've got to prove that m plus 1 isn't 0. You see, I've got a little goal here. How do I prove that m plus 1 isn't 0? But these are naturals, right? So this is suck. This is nat dot suck any 0 or something. Is that a thing? It says n. That is a thing. So this definition is compiling, but we've got some issue here. What's going on here? Why have we got this? Sorry, we're supposed to be defining an element of the positive natural numbers corresponding to 0, but we have this hypothesis that 0 isn't 0, right? And so we can solve this goal by just, I guess we could do kind of x falso, apply h, and now I've got to prove that 0 equals 0, and the proof of that is REFL. You see, so there's some, there we go. So there's my, that looks to me like a definition. So given a natural number that isn't 0, I get a positive natural number. And you see, here's the thing we want to prove really, right? Def of, so this is a theorem of nat add, right? Yeah. Theorem of nat add. And this would say, do you know, maybe it's just, I don't know. So let's have A and B in the natural numbers, of the x in the natural numbers, such that x isn't 0. There. And the claim is that of nat, and this would now be called, so now let's define of nat, def of nat primed. Of nat primed, and that will take an element of this thing here. I have A of this type, and I'm going to get a positive natural number, and it's going to be, because a term of type, this term like A is just a pair, a natural number, and a proof it isn't 0, so it's of nat, the first element of the pair and the second element of the pair. So of nat primed, so I now, yeah, you see, this is not so clever, right? Do you know what? I think maybe it's just easier. Let's go nuts. Let's do this. I think it might be easier just to use, do you know what? What about this? Def of nat. I'm going to call this double prime because I don't like it. I've gone off this because I'm sick of the hypothesis. I want it to return junk values. There, this is like 1 over 0 is 0. I think this is the best. This is the best function. Of nat goes from nat to p. There, and 0 can go to 37, of course, which is what? I mean, I haven't got. Well, maybe it's just easiest to go to 1, and 1 can go to 1, and n plus 2 can go to suc of nat n plus 1. So I think that's okay. So now of nat add, and so now I can just have natural numbers. So I could have a and b in naturals, and there better be nons. I mean, the point is you can evaluate of nat at 0, but it will give you a junk answer. So HA, A isn't 0. I can't resist this. Let's do 37. Where's my example? Let's define def 37. Let's define there, and now let's send this to 37, right? There we go. So this is the correct way to do it. So the hypothesis is that A isn't 0, and don't believe the computer scientists. B isn't 0. If your proofs are working in domains where they're not supposed to work, then you're not thinking about the maths in the right way. So of nat of A plus B is of nat of A plus of nat of B, right? Because if we can prove this, then we're somehow relating. We're relating the definition of column addition to the definition of natural number addition. And we could maybe use that to prove associativity, because associativity looks like it's going to be a real drag. But this is kind of interesting, because what this actually says, so this is actually a theorem, right? Theorem is that column addition gives the right answer. Right? I could have made some slip. I could have failed to, I could have put bit 1 suck at there. I could have made some mistake there, and then I can change that to that. Look at that. I changed the definition of addition, and add a soc 1 doesn't work, but it didn't work before. Because we hadn't finished it before, and everything else is working fine. But this theorem won't be provable because this definition of addition is wrong, right? Because I've said that two numbers that end in 1, you add them up and it ends in 1, right? I've done somehow a carrying wrong. This should be a 0, and this should be a 0. So maybe I've made some more mistakes, right? We haven't checked addition enough to know that this is true, really. So this theorem here is actually a check that column addition is actually defined correctly, i.e. we are formally verifying the definition of column addition. Well, the column addition algorithm, right? That's what we're doing. We're formally verifying the column addition algorithm because we're checking that it actually just it does actually, when you add up two binary nats which correspond to naturals, the result you get, you see this addition here is the binary nat one, and this addition here. So how are we going to prove this? Well, this is a statement about normal naturals. So I suspect that the only thing we can do is induction, really. So let's do induction. Well, I guess we should get rid of these cases. Case is A. We should just do a simple thing. You see, now we've got A can't be 0, so I don't really want to start my induction at 0. So cases HA ruffle, and then cases B, cases HB ruffle. HB ruffle. Because you see B, what's going on here is that B is a proof that 0 isn't 0. And so if you HB ruffle is a proof of false, because this says 0 equals 0 implies false. This is a proof of 0 equals 0. So HB REFL is a proof of false. So we can do cases on that, and there aren't any cases. That's what's going on there. And so now we can clear HA and HB. And so now this is what we've got to prove. And now the only tool we have really is induction, right? The only tool we have is induction. And in fact, the left-hand side is already at least 2, isn't it? Does that help us? My instinct is that we are not going to be able to do, are we going to be able to do this? Of nat suck A plus nat suck B. I want to somehow, this surely has to be proved by induction. This surely has to be proved by induction. And so do I do induction on B? Let's try. Let's try something simpler. Let's do, okay, addition is a complicated thing on binary. What are simpler things on binary nats? You see, suck is a simpler thing, right? Of nat, let's prove this. Theorem of nat suck. That says A is a natural, and then HA. HA is that A isn't 0. It says of nat A add 1 equals suck of nat A. There. And now we're going to prove this. Well, I guess we do the same. We do cases A. Have I still got this? We do cases A, cases HA REFL. That's the way to start it. And now maybe, can we do cases A again? Let's try cases again. Cases A. And now what have we got to prove? And hopefully this one is REFL. There. And this is a useless assumption. We've got to prove that of nat suck A add 1 is suck of nat suck A. Simp has not worked. REFL? REFL has worked. Oh, that's handy. Oh, so REFL works and simp doesn't. Does that mean that... That's interesting. Ah, I see. This, aha. It's because of this. That statement there. Where did we, this thing here, I see. The right hand side is suck of, this says of nat of n plus, of nat of A plus 2. So it's suck of nat n plus 1. Oh wow. I'm still slightly surprised that this works. Anyway, there's the mysteries of computers. So now I think maybe we're ready. So now can we attempt to do of nat add. So let's do it by induction. Induction B with DHD, generalizing A, probably. So, and now the base case is presumably, it'd be nice if it was REFL, wouldn't it? It's not REFL. Okay, right. So let's try and do this. Of nat dot suck A plus 1 is of nat dot suck A plus of nat 1. Ah, okay. So I see, I need some lemma, right. So here's a simp lemma. of nat 1. This is what I'm missing. This says of nat of 1 is 1, and it's true by definition. I see, and I see. Simp. I need this as well. Lemma of nat suck. This should be, simp should know this. This says, so this is A is a natural, and it says of nat of A plus 2 is suck of nat A plus 1. And that's also true by definition, right? There, because that's part of the definition. So now here, I wonder whether the simplify can do it. It can. So the simplify has done that, and it took some time to do it. So let's just sorry it instead. Simp works, but takes some time. And now what's going on here? I suppose we could just try simp HD. Let's just be optimistic. It's having a good think and it's failed. Right, so now we've got to do something then. So what's going on? We've got to prove. We've got to prove of nat of something. Oh, we've got to prove that of nat. Oh no, I see. We've got to prove that of nat of something. And what is this something? Is of nat a add 1. A add 1. It's a add 1 add nat suck d. So I think that's d add 1 add 1 equals something. Is that good? Yeah, that's good. And we've got to prove it's of nat a add 1 add something, and it's of nat. So of nat d plus 1 plus 1, which is by definition d plus 2. D plus 1 plus 1 is by definition d plus 2. So that's what we've got to prove. And I guess we need to use the induction hypothesis. Let's just try applying. Of nat d plus 2 is suck of nat d plus 1. Do you know what? So we could rewrite of nat suck, right? And then we get of nat this plus suck, we get add suck. And then here, of nat a plus 1, we've got this stupid suck. And so what we really need, we absolutely need add suck here. I think we need add suck. So we're going to have to do add suck after all. So where's add suck? So it's here, right? Lemma, it's a simp lemma. Add suck. So A and B, P. Let's do A add suck B equals suck of A add B. This is what we need. This is a special case of associativity. And my guess is that we're going to prove it by induction. Induction B with DHD. DHD generalizing A. And so the first goal is surely REFL. Let's try it. It's not. That's a bit annoying. A add suck 1 is suck of A add 1. So do I have to do cases? let's try the simplifier. What if the simplifier's done something? Oh. A add bit 0, 1 is suck. Okay, that sounds like a good simp lemma, doesn't it? Let's make this a simp lemma. And that is in fact this, isn't it? It's add a sock 1 1. So lemma, we've proved this already. So A add bit 0, add bit 0 1, add 2, AP. A add bit 0 1 equals suck of suck A, and that is by simp R. I should make this a simp lemma perhaps. And now can this be proved by simp? No, it can't. Hard luck. Why not? It's because this is not in simp normal form, I see. So we have to do some rewriting. So begin, end. A add bit 0, 1 is A add 1 add 1. So this is show A add 1 add 1 equals suck of suck A. And then we rewrite this way, add 1x suck, right? We need to get rid of the sucks. There, and we need to do it again. And now it's become A add 1 is A add 1 add 1. So now we can rewrite add a sock 1 1. Oh, do you know what? Could we have done that for a while? We could have done that maybe a while ago. We could do that here, and then, we could rewrite it that way here, there, and now the simplifier can do it, right? Because the simplifier knows the other tricks. Yes, the simplifier's done it. So there's add 2, and if we make that a simp lemma, there, then, and now this works, great. So add suck, the base case is now done. So now how are we going to prove this? For all A add suck D is suck of A add D. I think we just have to do induction on A now, right? Or we can maybe do cases on A. Let's do induction on A. Induction A with whatever, with CHC, and then let's just try simp on all the goals. And let's try, in fact, let's just try that same proof for both of them. Let's cut that and let's paste that. And now let's see what happens. So in fact, it worked for this one and it didn't work for this one. So how many? We've got 2 goals left. And what are our 2 goals? And the first one is, oh golly. We need to use the inductive hypothesis. So we should maybe do simp. Yeah. This is exactly HDC, right? Can I do this? Can I do HDC here? Does that work? No, I get an error because it's never heard of C in some of the branches. So we could try simp there, and then we could try simp, and then we could do this. And that's worked. Excellent. So there is our proof of add suck. You see, that's kind of interesting. I was putting it off, but actually the simplifier has done it all. Let's put a full stop there. We just had to figure out what the basic lemmas are. And so this is in some sense a lemma in training, a lesson in training the simplifier. And now finally, the thing I wanted to get to, let's prove this. So how are we going to do this? We've rewritten off nat suck, so now we can rewrite add suck. Rewrite add suck. And now we can rewrite HD. What exactly? Of nat suck A equals of nat suck D. So it's rewrite HDA, hopefully. Yeah, I've seen that fail before. Let's do this. So rewrite show. Let's say what do I want it to actually say? So I want to show this thing here. I want to show that this thing here. Oh, I'm rewriting it the wrong way. Do you know what? There is still hope. Does that work? Oh, it does work. Wonderful. And so now I've got to prove that of nat of something is suck of aha. Now, do we have of nat suck suck? So I can rewrite this. We have rewrite aha. Great. So we could rewrite of nat suck suck now the other way. We could rewrite this. Oh, I see I can't because it's not, this is not of the form something plus 1. Yeah, okay. So I have this stupid problem, nat suck A. I have this nat suck A plus nat suck D. So let's get rid of that. Rewrite show this thing here equals A plus D plus 1 plus 1. And so why is that true? There's just a tactic that does this, right? Omega will do this. Oh, by omega. Omega is our natural number tactic. And now we can rewrite. And now we can try congra. Apply congra fun or something. Apply congra arg. And now we've got to prove that we've got to prove this thing here, but this is a question about natural numbers where we have all the tooling. So there's omega. And that proof has compiled R, except it hasn't because there, what about that? And let's put a dot at the end. So this might take, oh, there we go. That was relatively quick. So that proof is compiled. It's because I've got better simp lemmas. That proof is compiled. And this is a proof that column addition is the same thing as a unary, as natural number game addition. And hence you could imagine that we could prove associativity in this new way, except we're going to have to probably write a map in the other direction and prove that this is true for the map in the other direction as well. But you can kind of begin to see how to, I don't know, just how to set up a theory in Lean. And I think it's quite interesting. So I guess I'll stop there. Thanks for watching.